The development of an ultra-thin magnet that operates at room temperature could lead to new applications in computing and electronics, such as high-density compact spintronic memory devices and new tools for the study of quantum physics. The ultra-thin magnet, which was recently reported in the journal Nature Communications, could make big advances in next-gen memories, computing, spintronics, and quantum physics. It was discovered by scientists at the Department of Energy's Lawrence Berkeley National Laboratory and UC Berkeley. The researchers said that they are the first to make a room temperature 2D magnet that is chemically stable under ambient conditions. This discovery is exciting because it not only makes 2D magnetism possible at room temperature, but it also uncovers a new mechanism to realize 2D magnetic materials. The magnetic component of today's memory devices is typically made of magnetic thin films, but at the atomic level, these magnetic films are still three-dimensional, hundreds or thousands of atoms thick. For decades, researchers have searched for ways to make thinner and smaller 2D magnets and thus enable data to be stored at a much higher density. Previous achievements in the field of 2D magnetic materials have brought promising results, but these early 2D magnets lose their magnetism and become chemically unstable at room temperature. State-of-the-art 2D magnets need very low temperatures to function, but for practical reasons, a data center needs to run at room temperature. The researchers say that their 2D magnet is not only the first that operates at room temperature or higher, but it is also the first magnet to reach the true 2D limit. It is as thin as a single atom. The researchers say that their discovery will also enable new opportunities to study quantum physics. It opens up every single atom for examination, which may reveal how quantum physics governs each single magnetic atom and the interactions between them. With a conventional bulk magnet where most of the magnetic atoms are deeply buried inside the material, such studies would be quite challenging to do. The researchers synthesized the new 2D magnet called a cobalt-doped van der Waals zinc oxide magnet from a solution of graphene oxide, zinc and cobalt. Just a few hours of baking in a conventional lab oven transformed the mixture into a single atomic layer of zinc oxide with a smattering of cobalt atoms sandwiched between layers of graphene. In a final step, graphene is burned away, leaving behind just a single atomic layer of cobalt-doped zinc oxide. It is potentially scalable for mass production at lower costs. To confirm that the resulting 2D film is just one atom thick, the research team conducted scanning electron microscopy experiments at Berkeley Labs Molecular Foundry to identify the material's morphology and transmission electron microscopy imaging to probe the material atom by atom. With proof in hand that their 2D material really is just an atom thick, the researchers went on to the next challenge that had confounded researchers for years, demonstrating a 2D magnet that successfully operates at room temperature. X-ray experiments at Berkeley Labs Advanced Light Source characterized the 2D material's magnetic parameters under high temperature. Additional X-ray experiments at SLAC National Accelerated Laboratories Stanford Synchrotron Radiation Light Source verified the electronic and crystal structures of the synthesized 2D magnets. And at Argonne National Laboratories Center for Nanoscale Materials, the researchers imaged the 2D material's crystal structure and chemical composition using transmission electron microscopy. As a whole, the research team's lab experiments showed that the graphene zinc oxide system becomes weakly magnetic with a 5 to 6% concentration of cobalt atoms. Increasing the concentration of cobalt atoms to about 12% results in a very strong magnet. To the researchers' surprise, a concentration of cobalt atoms exceeding 15% shifts the 2D magnet into an exotic quantum state of frustration, whereby different magnetic states within the 2D system are in competition with each other. And unlike previous 2D magnets which lose their magnetism at room temperature or above, the researchers found that the new 2D magnet not only works at room temperature but also at 100 degrees Celsius. When you command your computer to save a file, that information is stored as a series of ones and zeros in the computer's magnetic memory, such as the magnetic hard drive or a flash memory. And like all magnets, magnetic memory devices contain microscopic magnets with two poles, north and south, the orientations of which follow the direction of an external magnetic field. Data is written or encoded when these tiny magnets are flipped to the desired directions. Zinc oxide's free electrons could act as an intermediary that ensures the magnetic cobalt atoms in the new 2D device continue pointing in the same direction and thus stay magnetic even when the host, in this case the semiconductor zinc oxide, is a non-magnetic material. The researchers say that the new material, which can be bent into almost any shape without breaking and is 1/1,000,000th the thickness of a single sheet of paper, could help advance the application of spin electronics or spintronics, a new technology that uses the orientation of an electron's spin rather than its charge to encode data.